Thanks, Phil, for the introduction, and thanks for having me. And today I'm going to talk about a stationary set method for estimating oscillatory integrals. So before I forget, this is all joint work with Saugata Basu, Shaoming and Pavel Zorin-Kranich. So I think some of them are here or will be here shortly in the audience. So this is a plan of my talk. It has a lot of stuff. But hopefully I will be finishing on time. So I'll be introducing various aspects on oscillatory integrals that are related to today's talk. So this is a vast subject. It's impossible to make a comprehensive introduction, but I'll say what's mostly related, in my opinion. And then I'll be introducing the main result, which we call a stationary set method. And then we'll introduce an application to the so-called convergence exponent problem. And we use this method and additional considerations, obtain sharp results in there in dimension 2. So I'll also mention a little bit about why we can only do dimension 2 at this point. And then, yeah, in the fourth part, so you can see the fourth part and the sixth part are the proofs. Overviews. So the fourth part concerns this application. So I'll say a little bit about what we do in addition to the main theorem so that we get the sharp results in dimension 2. This involves understanding the so-called stationary sets in the two-dimensional case. And then this thing has a nice corollary. That's the sharp L infinity to Lp Fourier extension estimates for a family of two-dimensional surfaces, which I'll also briefly mention. And then in the end, I will go back to the proof overview of the main theorem, which I chose to place at the end because it has a slightly different flavor than the usual flavor of this kind of problems. So we have to use, turns out we have to use so-called O-minimal geometry to make this like a proof of the bound. So hopefully this will be interesting. This will be interesting to both analysis and number theorists. Actually, this convergence exponent problem in the so-called Tarry's problems has motivation in number theory. So I'll talk more about it when we see the actual problem. Just feel free to ask questions or interrupt me at any moment. Hopefully, everything will be clear. I don't have any prerequisites for this talk. Okay. So starting with the oscillatory integrals, well, such an integral that I write here is a typical oscillatory integral. So it has two parts. It's an integral of a product, and the product involves e to the I phi, which is oscillatory, and that's why you have the name when phi is real. So our phi will always be real, and you have a cutoff function psi. So you can take psi to be a smooth cutoff or a sharp cutoff. We'll see various cutoffs throughout this talk, and it naturally shows up in a lot of situations. I think in Fourier analysis, PDE and number theory, spectral theory, and mathematical physics. One key phenomenon about this kind of integrals is that it's really bad to use triangle inequalities to estimate them. So their absolute value is usually much smaller than the L1 norm of psi, even though if you take the absolute value inside the integral, you will get the L1 norm. And this is a concrete example I usually give to my students in analysis. So if you take an integral from 0 to 1 of e to the say 10,000 times I times c, and then you see the magnitude is approximately 10 to the minus 4 by integration by parts, very simple argument. I show it in the next slide. But if you want to use triangle inequality to estimate, then you have a really poor estimate. You just get 1. So this is pretty bad. And in general, you see more rich phenomenon than just you bounding it by triangle inequality. Okay, and so I wrote down a quite general class of oscillatory integrals, but one typical thing people usually study first is the so-called one-parameter oscillatory integrals, which also shows up a lot in various contexts. So here, your phase function is I times lambda times phi. So you fix the phi, and then you make your parameter lambda being real, going to infinity. And there are two key questions people usually care about. So the first is that how I of lambda decay when lambda goes to infinity. So you already saw a hint of that in the previous example, but there are more rich phenomena. People also care about the asymptotic behaviors, but that will be less related to this talk. I also mentioned it a little bit in the following few slides. So in the one-dimensional setting, meaning that if you take this D to be 1, then we have a relatively complete theory or understanding of this one-parameter oscillatory integrals, and in general, a lot of other oscillatory integrals. So I take the following 3 slides from Eli Stein's book, Harmonic Analysis. These 3 principles are sort of the main phenomenon you can see in the one-parameter oscillatory integral questions. So the first one is known as localization. It's quite simple. It's also a consequence of integration by parts. Well, it says that if you have one-parameter oscillatory integral, and your phi and psi are smooth, and phi is real, psi is a cutoff. And if you happen to have phi prime being non-zero on the support of psi, then with lambda going to infinity, your integral is going to decay faster than the reciprocal of any polynomial, so faster than lambda to any minus capital N. So this follows by repeated integration by parts, and sees a lot of applications already. But an interesting consequence of this is that if you have a general phi, then what you can do is you can use a partition of unity to decompose the support of psi, and then this will show that the decay properties of this I of lambda is actually dictated by the positions where phi prime vanishes, because when phi prime doesn't vanish, you can repeatedly integrate by parts and make the contribution arbitrarily small. So the decay properties only depend on the integral around the zero set of phi prime in the general situation. So that's why it's called localization. And what's going on when phi prime is 0? Well, things will behave a little differently. And this principle, I think in Stein's book, is known as scaling. I guess it's because you can rescale the picture to like a nice one that you know. But it's stated as the following. So here I will take psi to be a sharp cutoff, being the cutoff of the interval A to B. I guess the similar situation would show up if you have smooth cutoff. But if you have a phi that's a phase function now, and well, its derivative might vanish. So what is a good model of a phi? Well, you can take, for example, c squared or c cubed, etc., etc. And you observe that for those phase functions, you would have some derivative non-vanishing. And this is also known as van der Corpus lemma, saying that if you have such a property, if you have the case derivative of phi is always bigger than or equal to 1 on the whole interval from A to B with k at least 2, then you will have this integral to be big of lambda to the -1 over k. So that's perhaps a less trivial exercise in analysis, and it's proved by induction and decomposing the integral into 2 parts and estimating the 2 parts differently. And one very nice thing is that this exponent 1 over k is sharp in general, so that, for example, if you integrate it with phi equals to c squared, you will see -1/2, and you cannot hope to improve this. And this can be seen by, for example, an approximation using complex analysis. And the study of this will lead to the third principle, which is asymptotics, which says that if you have a phi and psi, they're both smooth, and you assume the support of psi is sufficiently small near an interesting point in terms of phi. So this point is x0, and assuming phi prime of x0 is equal to phi prime prime is until phi of the k-1 derivative, assuming they're all 0. But the case derivative of fx0 of phi is not 0. And now you require the support of psi to be sufficiently small to capture only the interesting behavior around this point. Then you would have a very nice asymptotic expansion of this I of lambda, which I showed you. And this is one expression of the method of stationary phase. So very nice theorem and very complete understanding in this situation. Okay, so you can use these 3 principles to understand a general one-dimensional oscillatory integral, which leads to a lot of good understandings of them. But what about higher dimensional oscillatory integrals? Well, things quickly get much nastier. So, well, the localization principle is still good. So you can, for a general higher dimensional oscillatory integral, you can still decompose psi to localize the problem. And you still have the fact that the gradient of phi, as long as it doesn't vanish, you can integrate by parts, and hopefully you will have a small contribution. And the places where the gradient of phi vanishes are most interesting and makes the most of the contribution to the integral. So remember, our primary concern is to get an upper bound of this oscillation integral. And it's much more difficult and especially complicated because phi can have very complicated degenerate critical points. So if all the critical points of phi are non-degenerate, you will have a roughly better idea of how big this I is. But if you're allowed to have degenerate critical points, which you have to allow in the general situation, things will quickly become very complicated. And so if we are back to the one parameter setting, you can look at the one parameter oscillation integral. And what's some simplest phi you can look at? Well, you can look at polynomial phases. So polynomials are the simplest non-trivial smooth functions. So you can look at a one parameter oscillation integral with the phase to be lambda times a fixed polynomial p. And then how would this behave as lambda goes to infinity? Well, there's a general principle known as Arnold's hypothesis, which has been verified by a lot of work by Varchenko and then Greenblatt, etc., that the decay rate of this has to do with the Newton polyhedron, which is something I haven't told you, but unfortunately I wouldn't have much time to talk about this today, but you can imagine it has something to do with algebraic geometric tools, for example, and this is very mysterious and very nice discoveries by Varchenko and Greenblatt and various other people. But my focus today will be, what if we're not looking at this one parameter situation? What if the phase, you just know it's a polynomial of a given degree, for example, of just degree 100, and it might depend on multiple parameters. And then this situation is not that well studied to my knowledge, and I'll just mention a few related, I think, previous results. I think Karpushkin proves stability results in 2 dimensions, meaning that in certain situations, if you perturb the phase a little bit, then the decay rate wouldn't, I think, wouldn't change. And von Stein-Sturm has a follow-up study in 2 and 3 dimensions, but they studied slightly different stability results to my knowledge. And also, I've talked about this van der Corpus lemma, which is the most interesting component in the one-dimensional phenomenon. But there's a very nice higher dimensional van der Corpus lemma discovered by Carberry, Christ, and Wright, saying that if you have a derivative, a mixed derivative, that's always greater than 1 on your integration domain, then you will have very nice decay rate estimates. Actually, if you assume the phase is a polynomial of a given degree, this will actually match the best you can imagine. So very impressive. but it's also only useful if you have a global lower bound of a mixed derivative, which doesn't hold in all the situations. Our research project actually has a lot to do with this kind of previous work and the motivation, but we have another motivation, which I'll get into in a bit. But we are, in our project, we are led to study this question, quite general question, but also kind of ambiguous to start with. So if you have a real polynomial in d dimensions, assuming its degree is less than k, so d and k are completely arbitrary. You just give me the numbers, like in 10 dimensions of degree less than 100, that's okay. Then I will ask the following question. What is the good upper bound of this integral over the unit cube 0,1 to the d of e to the 2 pi I p dc? So what is the good upper bound? And so we have a new discovery that's quite unified and not too difficult to state on this question. And we found some bound that has a geometric interpretation, and it's good in a lot of cases. So that's the main thing I want to talk about today. And I think to be more accurate, we have a motivation of this bound, actually. So that's in the next slide. So in general, if you have an oscillatory integral, well, the phase will oscillate, assuming you have a sharp cutoff function for simplicity. And then your phase will oscillate. And it's a very elementary observation that if your phase oscillates in, say, 1/3 or 1/2 or 1/4, doesn't matter, of a period, I guess I said 1/3 just because I want, for example, the real part, or they all concentrate in the same direction. So within 1/3 of the period, the contribution of the integrand, they don't cancel. They're just pointing roughly in one direction, if you think about it in the complex plane. Then you will see that the contribution of that part has to be at least roughly the measure of C, where your P is within a certain 1/3 of the period. So you might think, if you're optimistic, then you might believe that there can be no more constructive interference beyond this range. You just believe everything beyond, say, 1/3 or one period must miraculously cancel if you have good assumptions. And this was one motivation that we started to form a conjecture. And I'm going to make it more formally here. So this motivated us to define the so-called stationary set. So how is it defined? If you have a polynomial P, then I define the stationary set L of P to be supremum of all the mu such that, well, the measure of C such that P of C is between this mu and mu plus 1, so within one period. So I have this normalization factor 2 pi I to just make it stay nice. So L of P is the supremum of mu such that it's the supremum of the measure of C such that those C is satisfying P is between mu and mu plus 1. So within one period. Within one period is roughly the same as within 1/3 of the period when you take the supremum. So it doesn't matter. And as I explained in the last slide, if we're optimistic, we can hope this integral is controlled by the stationary set. And this is indeed true when P is a polynomial of bounded degree and of bounded degree in a given dimension. And that's our main theorem. So I'll state it in the next slide. So formally, the theorem reads the following. If you have a real polynomial, has to be real in d dimensions with degree bounded by k, and you define the stationary set to be like what I explained before, then this integral over 0,1 to the d of e to the 2 pi I p has to be bounded by the measure of the stationary set up to a constant depending on the degree and the dimension. And that's the main theorem. So maybe let me, because this is the main theorem, let me pause a little bit and see if there are questions. Okay, good. So I just want to make sure that we have no problem understanding the statement and a little bit of remarks and connections to previous results. So I want to emphasize that the implied constant depends on D and K, but not on P. It will be uninteresting if it depends on P. So it's uniform with respect to all the polynomials. I'll say that it's sharp in the larger classes. Probably, I don't know if I have time to explain the exact meaning of that, but there's a third remark that the only proof we know uses something that's a little bit unusual, uses the theory of all minimal structures. I'll explain in the end a little bit. Okay, so this is like not completely out of nowhere. I'm going to explain some of the connections to previous thoughts by people. So if you know about sublevel sets, those are what's between the level sets of a function. You notice that our station sets are a kind of sublevel sets, and people actually have discovered that they have close relationship with the bounds of oscillatory integrals already before. My understanding is that most of the time, a lot of approaches that's developed by people will apply equally well or approximately as well as the other, estimating sublevel sets and estimating oscillatory integrals. But there's indeed one connection on the rigorous side, that if you have a good oscillatory integral estimate, then sometimes you can get good sublevel set estimates. If you're in the one parameter setting, this will depend on the decay. This will depend on the decay rate. Usually in the slow decay region, you will have this. And this is by what I call completing the integral in the spirit of number theory. Basically you see that if you have a sublevel set, you want to estimate it, then basically you have a sharp cutoff. And what you can do is to dominate this sharp cutoff by a smooth cutoff of the function value. And because you have a smooth cutoff, you can expand it by Fourier transform. But once you have the Fourier transform, you will see various oscillatory integrals. And then it's just a band limit function. And then if you have good oscillatory integral estimates, you just integrate the estimates and you recover the sublevel set estimates. But one very curious and very nice thing that I found is that our theorem goes in the opposite direction. And as I explained, that there are certain good heuristics. There are heuristic reasons why you can go in the opposite direction, but it's not very often that you can rigorously control the oscillatory integrals by sublevel set estimates. And so far as I know, there's indeed one previous result related to our theorem, but it's in another setting. So I'll introduce that in a few slides. But for now, those are just the comments between sublevel sets and oscillatory integrals. And let me first introduce an application. That's our main application of this method. I believe that's in our next slide. Yes. So now we turn to a very concrete problem that has the number theory motivation. So we're fixing the dimension and degree. And what I'm considering, we have a lot of monomials in this dimension with degree less than k. And we have a distinguished map from Rd to R of capital N by just writing down all the monomials, C1, C2, until you have CD to the k's power in D variables of degree less than k. So this, we have a map that I call it phi of dk. And S of dk, it's going to be the resulting manifold when you map the unit cube under phi of decay to this R to the capital N. So I think in this talk, I'll abuse the notation a little bit. I'll call SDK a surface. So when I say a surface, it doesn't mean a two-dimensional object. It just means a submanifold. I think this is because of some terminology in the existing literature. So I'll stick to that. So SDK sometimes is known as Parsell-Vinogradov surface. And you can associate a Fourier extension operator to it. Unfortunately, because of time, I don't have more time to motivate the Fourier extension operator, but I'll just say that it's an important object in Fourier analysis. So this E, this operator is defined as the following. If you start with the function f on the unit cube in d dimensions, then you integrate it against e to the 2 pi x dot product with phi. So x is in R of capital N rather than a small dimension of dc. So you formally define this operator. It also has a geometric meaning that if you have f, then you can push a measure f of c dc onto this Parsell-Vinogradov surface SDK, and the extension operator just shows you what the Fourier transform of that push forward measure at any point x is. And this also has a very nice feature, a nice connection to our previous problem, that our previous motivation, that if you take x dot product with phi dk, you get a polynomial that's that has degree less than or equal to k in d variables. So for each x, you get a different polynomial, and all the polynomials without constant terms can be described by this. Well, I require them without constant terms because I want to see certain decaying property. That's the motivating question, known as the convergence exponent problems in Tarry's problems. So first studied in number theory, I guess this is the oscillation. This is the so-called, I think, singular integral in number theory when you study Tarry's problems using the circle method. So this is first raised by Lu Kenhua in 1952. And then that was in the case dimension equals to 1. And then Arkhipov, Chubarkov, and Karsuba resolved the case when d equals to 1 and raised the question in general dimensions. But this is an interesting question from the perspective of harmonic analysis, of course, that can you determine the range of P such that E of 1 is in LP? So trivially, it's in L infinity. So what is, I'll explain that 1 of 0, 1 to the D, it's just a characteristic function. So it's sort of the Fourier transform of sort of canonical surface measure, with some normalization, but basically the surface measure, and you want to ask which LP space does it belong to? And trivially, it belongs to the L infinity space. And if you know a little bit about uncertainty principle, you know that the smaller P is, the more challenging this problem becomes. And the question is actually really determining the smallest P such that this is in LP. And I require no constant terms because I want some non-trivial P. Like if you think about it, if you allow to include constant terms, then along that direction, this E of 1 doesn't decay completely, and you won't be able to put it in any non-trivial LP. But by excluding the constant term, it's possible to put it in some non-trivial LP. So that's the difficulty and interesting part of this question. Okay, so let me explain some results we are able to prove using our method. Okay, so this is just a reminder of the question. And our theorem just says that we completely solve this question when the dimension is equal to 2. So E of 1 is in LP is equivalent to P bigger than some critical exponent, which you don't need to pay too much attention on. So as I said, the case when dimension is equal to 1 is resolved by Arkhipov, Chubarkov, and Karsuba, and also Drury in a different setting with a slightly stronger estimate. And the case when K equals to 2, so K is the degree, is known by Monkenhaupt, I think, in his thesis. He actually resolved the case when K is equal to 2 and in all dimensions. So for degree 2 case in all dimensions, this is known. But our results says that when the dimension is 2 and you're allowed to have, say, degree 100, and then you still know the optimal LP spaces. So this is our result. And based on our method, we just need to prove something about stationary sets because, as I said, E of 1 is just the oscillatory integral that's in our main theorem, right? So when for each x dot product with phi is a polynomial, and we fall into the range where we can apply our theorem. So this integral is bounded by some stationary set measure function, and then we just need to prove that thing is in LP as well. So that is indeed in LP, and this is a quite general phenomenon when P is bigger than capital N. So you have to, that has to be in LP when you replace the oscillatory integral by the stationary set. That's why I say it's sharp in various settings, but I probably don't need to, I don't have time to explain that, but I'll just say that, so nevertheless, I can show you how we proceed. So we have this phi, and we define the stationary set function. So for each x, we choose a mu such that the measure of C, where mu is less than x dot phi dot less than mu plus 1, is maximum, and we call this the stationary set. Well, if there are multiple mu's, we just choose one. And then the question will become, for each x, you have the measure of the stationary set. So this is the measure of C of x. And we prove that for P bigger than the critical exponent, this measure function is in LP. And as a corollary, because of our main theorem, we know that E of 1 is also in LP and complete the hard part of our theorem. So this is just this is just how we proceed in proving this theorem. Of course, I haven't told you much like why we can prove the function Z of x, this measure is in LP. Well, it's totally unclear at this point. Well, I'm going to tell you a little more thoughts, but before this, let me just mention there's a geometric interpretation of stationary sets that I like to say at this point. So yeah, this picture is drawn by my friend Zorin-Kranich Zhang. So thanks to him. And as I said, we are looking at the Fourier transform of certain surface measures. So you can actually interpret your stationary sets in a geometric setting. So when you look at the Fourier transform of a surface measure, as what I explained before, at a certain point x, what you can do is you first take an infinite slab that's perpendicular to the direction of x. And then you take its thickness to be 1 over the norm of x. And then you just move this slab around in the frequency space, like you intersect your surface with this slab. And what is the stationary set? It's just the largest possible intersection between this surface and the slab. So for each x, you can find the stationary set using this geometric way. And I mentioned this because this enables me to mention the related result that I haven't told you. So there's an earlier result by Bruna Nagel and Steve Wenger, which I very gladly have in the audience. So they proved in 1988 of a similar form for convex hypersurfaces of finite type with respect to the surface measure, meaning that, so they're studying the Fourier decay of the surface measure of convex hypersurfaces of finite type in any dimensions. And they obtain a result that's similar to ours in this geometric sense. So their bound will correspond to the case when the slab is tangential to the hypersurface. So meaning that you take the intersection of the slab with the surface in one end where the slab is tangential. And in comparison, our result can generalize to a situation where the implied measure has bounded complexity, which I described in the last 2 lines. But it's quite general. You don't need to assume the codimension, the convexity, the finite type, etc., etc. But one thing that sometimes will be a disadvantage is that our results need a comparison between all the positions of the slab. So you don't immediately have when the slab is tangential at one end of the hypersurface, you actually have to move the slab around in the space and compare and look at the largest intersection, and that's our upper bound. So, so just a little comparison and a little bit of history. So the bounded complexity just means things can be defined, described by a bounded number of polynomial equations or inequalities of bounded degree, which we'll return to in the end about the proof of the main theorem and see why we need this. Okay, so my plan next is to say a little bit of words about how we proved this critical exponent. This measure is in the LP space. So, okay, so the next 4 slides are probably the most technical part of this talk, and I'm happy to explain if you have any questions. Okay, so let's recall the setting and the problem a little bit. So we have this phi, and we have this stationary set measure, z of x. For each x, you define z of x as in the second line. So take the maximum over mu over all the measures of c such that x dot phi, a polynomial, is between mu and mu plus 1. And our goal is to prove this stationary set measure function, z of x, is in LP when p is bigger than the critical exponent. Okay, so what's a common strategy of doing this? Well, z of x is always less than 1, so you just need to care about the decay around infinity. Of course, it might decay differently in different directions, but a common way to prove such an estimate is you take a dyadic delta, and you just look at those x such that z of x has a measure between delta and 2 delta, and I call this collection of x to be L of delta. And it suffices to prove L of delta has a measure less than delta to the minus p2k minus some epsilon of room on the exponent. So this is a standard thing to do. And as I said, we already used our main theorem. So the next few slides doesn't have to do with the main theorem. We already reduced the convergence exponent of the oscillatory integral to this problem that doesn't have any oscillation. Okay, so what did we do? We first made an observation that if your stationary set has a measure roughly delta, so I'm drawing the, for example, 2-dimensional unit cube, which is a unit square, and the pink part is my stationary set. So the first lemma that's stated in the not in the most rigorous sense, is that if your stationary set has a measure as large as delta, then this cannot look too spread out. For example, cannot look like a fractal because you're in a bounded degree situation. Then you know this stationary set is morally a union of lattice delta cubes, as I drawn in red. So you can sort of have a more concrete grasp of the stationary set when it has measure roughly as big as delta. So that's a good thing. And the next thing might feel familiar if you work on Fourier restriction type problems, but it's a very nice new discovery in this setting. So you fix capital K depending on the epsilon. Remember, epsilon is that extra room on the exponent. So when stationary set has a measure roughly equal to delta, stationary set is drawn to be red in this picture. We have 2 cases of the stationary set. So in the first case, it's concentrated into a vertical strip of length 1 over k, and we call it concentrated case. And the other case is that it spreads all out on the unit cube. So we call it the Spreadout case. And we can bound the measure of all x in the concentrated case by the so-called induction on scales. So you can probably imagine how this is done if you work on Fourier restriction, but I won't have time to say much about this step. But the Spreadout case is the most interesting. And I have a very involved slide next. Hopefully I can give you some sense of how we dealt with the Spreadout case. And this is the main technical part, I think, that why we can prove the two-dimensional problem completely, but cannot prove the sharp exponent in 3 or higher dimensions at this moment. Okay, so how do we deal with the Spreadout case? So remember, for each x, I have a stationary set, and I'm gathering all the x where the stationary set corresponding to x is in the Spreadout case. How do we deal with it? Okay. So what we do is that we just find a constant number of vertical delta strips that are roughly 1 separated, such that I take all the x in the Spreadout case, and for a positive proportion of them, each strip, remember each x has the stationary set with measure roughly delta, so it has to be roughly a union of delta cubes. So where are those delta cubes? Our strips satisfy that each strip contains 1 square in two-dimensional case that's essentially in this stationary set. So what do we know about x when you have those squares? Well, consequently, you know, for example, for an x, your stationary set is contains the 3 red delta squares as shown in my picture. Then x has to be in the dual box of the convex hull of the corresponding 3 red caps on the surface. So that's just a simple geometric observation. If you think about the geometric picture I gave you a while ago, that's just a simple geometric observation. And what we do is just we enumerate all the possibilities of the k+1 tuple. So the 3 tuple just has delta cubed many possibilities in the degree 2 case. And well, you know that a positive proportion of the Spreadout x has to be in one of the situations. Well, in each situation, x is in some box. So a positive proportion of the Spreadout x is contained in the union of all the boxes. And then I just can simply compute the sum of the volumes of all the boxes. And then if that gives you the right exponent, then we're done. And we are very fortunate that we proved the two-dimensional situation in this way. So the numerology just works out. And that's very satisfactory. But in 3 dimensions, if you want to follow this path, you will have new difficulties. And we are trying to figure that out, but seems quite different from the two-dimensional situation. Okay, well, this is kind of technical, so let me stop and ask if you have any questions on this very crash description of the proof sketch. Okay, so let me quickly say a consequence that's in the Fourier restriction theory that I also found kind of intriguing. Again, so I don't have enough time to start over to motivate for extension estimates, but we have this Parsell-Vinogradov surface. We have the Fourier extension operator, and our result has a consequence in the Fourier restriction theory. So the theorem is what I just want to remind you that you have E of 1, it's in LP for some sharp range of exponent of P. And one interesting consequence is that if the endpoint of P is an even number, that's when K is not congruent to 1 modulo 4. So if you happen to be in Schipperen's talk last week, he has something very similar, and this works out 3 out of 4 times. So very nice. We are not claiming something that's not in an empty set. Then we know that for p bigger than this same critical exponent, E of f for any f in L infinity, E of f, the LP norm of E of f is bounded by the L infinity norm of f. So this range of p is also sharp. And so the trick is quite simple. So from this theorem to the corollary, you just notice that when p is even, you have Planck-Real, and then you just need to prove it for one f that's roughly 1 everywhere, and then you can bound this E of f by E of 1 by Planck-Real if p is even. So that's a simple trick, but this is a very nice corollary that it has certain connections to other parts of the literature. So let me elaborate a little bit on this. Also, so a little bit of history. When d equal to 1 is proved by Drury, Drury actually also proved slightly stronger results. So the difference between Drury's result and, for example, Arkhipov, Shubakov, Karasuba's result is that they only have 1. And yeah, so they only have 1. So when p is odd, they cannot prove it, at least superficially from the result. But Drury proved all cases. And when k is equal to 2, this is proved by Monkenhaupt. But when k, I think when k is equal to 2, p is always even. So these two are morally equivalent. So what we're able to prove is that when the critical point is even, when dimension is equal to 2, you always have the sharp L infinity to LP restriction estimate. So one very curious thing I want to mention is that, as you can see, there are a lot of recent developments proving Fourier extension estimates. Especially if you work in this area, like all the tools I listed here. So initially we wanted to apply some of the tools to prove this theorem, and indeed we are able to recover Monkenhaupt's result. I think that's in another joint work with so Shaoming, Pavel, and Changgen, also Changgen O from medicine as well. When k is equal to 2, but unfortunately, a very curious thing also is that if we want to apply them to get the sharp range of p for a degree bigger than 2 in even 2 dimensions, we had great difficulty. So we have certain steps we don't know how to proceed. So we didn't succeed in applying them to get sharp p. And but however, some parts of our proof, as you can see, for example, the concentrated part, if you know Bergen-Guth iteration, you might feel they're kind of similar. So they do feel analogous to certain approaches listed above. So I don't know, maybe those are two different parts of a slightly bigger picture. I mean, I'm quite curious about it. Okay, so this is just our a consequence on the Fourier extension result. And for the remainder of the time, I think I'm going to say a little bit about how we prove the main theorem, which is also conceptually not too bad, but very curiously have to involve new ingredients. Okay, so let's be back to the main theorem. Okay, I just stated here to remind you what the theorem is. And actually, the conceptual idea that we use to prove this theorem is extremely simple. So you want to prove an upper bound of I of p. I of p is some integral of something with absolute value 1. So you can change this into an integral that's in one variable. So you collect all the xi with p of xi being the same value, and then that's an integral in one variable. But and the phase function is very nice. You get 2 pi x as a phase function. But the cost you pay is that you're integrating 2 pi e to the 2 pi x against some other function, which you might not know too much about. And as I said, the whole point, I think the whole point I like about this theorem is that it avoids to use singularities. It doesn't use too much of algebraic geometry, but still gives you strong applications like what I just mentioned before. So that's the one thing we like. So we don't want to go into the singularity theory, for example. But we still need to know something about the polynomials, and that's the route we take. So we're in the one variable world. What kind of things we have to know about that weight we integrate against the e to the 2 pi x? Well, if you have the fact that that thing changes monotonicity bounded many times, then you can actually integrate by parts, just like the argument I showed you in the beginning. But you have some weight function, but you know the weight function changes monotonicity bounded number of times, so you can still do the integration by parts with respect to that weight function. And then indeed, this is the conceptual way we prove the theorem. So as I said, the conceptual proof is not too difficult. As long as we have that monotonicity lemma, you'll be able to integrate by parts. So that's what I put in the last remark of this slide. You just need a geometric lemma, and it's about semi-address sets, which I'll explain, I think, in the next slide, what those are, that are related quite closely with polynomials. Okay, so this is the lemma we need, and to prove this lemma, we use some all minimal geometry tools, which I'll show you in two slides. So a semi-address set is a generalization of algebraic sets, which we're more familiar with. It's just a finite union of subsets, each of which is defined by formula form some polynomial equals to 0, some polynomials bigger than 0. So this kind of formula. So for example, the closed square is on the plane is a semi-address set. Even if you put into R3, it's also a semi-address set. So each P and Qj, those are polynomials. And we can loosely define the complexity of such a set. I define it to be the minimal possible sum of all the degrees of polynomials showing up in the definition. You can choose your favorite definitions, but usually for a reasonable definition, the notion bounded complexity is well defined, meaning that you can take some semi-address set of bounded complexity. That's, for example, of complexity. For example, that might mean you take a semi-address set that might be defined by less than 100 equations, less than 100 inequalities, and less than 100 unions, where all the polynomials have degree less than 100. So that's one possible set of bounded complexity. And the lemma we need is that if you have a semi-address set in n+1 dimensions, so you'll see why I set it up this way, and of complexity less than C, so bounded complexity, then you can look at the slice of this set. You can intersect this set with a hyperplane, xn+1 equals to y, and you move this hyperplane around. So this is always parallel to the coordinate 1 to n hyperplane, but you move it up and down. And you take the slice, that's the intersection, you take the volume. So I call it the slice volume function. And what I need is that, say, our semi-address set is bounded. And we need that it changes monotonicity bounded many times. This bounded big O of 1 depends on the dimension and the complexity, but nothing else. That will be the case when we study this polynomial of bounded degree setting. So this, so the measure is the Hausdorff measure on this hyperplane. And in the next slide, I show you a more intuitive picture of what you should be thinking about. So as I said, the closed square is a semi-address set. So what is the slice volume function? I draw it sort of vertically. When you take the slice, first you see nothing, but when you touch the square, you start to get some increasing, you start to get it increase. And then for this position, you see it stay there for a while and then start to decrease and eventually disappear. So this is a very concrete slice volume function. And you see this function changes monotonicity one time. So it first increases and then decreases. And our task is to prove that this is true in general, and it's uniform in terms of the complexity. So that's a crucial thing. So I have my last slide, which has a summary of what we do to prove this lemma, and has some interesting ingredients from all minimal geometry and why we need it. Okay. So we don't know any elementary proof. We have to use all minimal geometry. We think about the problem, we can start with the following. Since we deal with semi-algebraic sets, we might want to look at a class of functions known as semi-algebraic functions. Those are just functions whose graphs are semi-algebraic sets. And we know that they obey good rules such that if you have a semi-algebraic function in one dimension, then it has to change monotonicity bounded many times depending on the complexity. So that's what we know. But things are a little bit trickier. So this is enough if remember we were in R to the n plus 1. If n is equal to 1, then this will be enough. But when n is at least 2, we will see some sort of integration over our hyperplane because we are looking at the volume. The volume is just a typical integration. In general, if you integrate a semi-algebraic function, then it's not preserved. So we all know, for example, the well-known example of elliptic functions. And then you're not semi-algebraic anymore. But it's very fortunate we have very powerful tools that the integrated functions, they still belong to a good family. And the members of this family still satisfy good uniform monotonic properties in one-dimensional subspaces. So I have two statements that they belong to a good family. So this is proved by Cluckers and Miller in 2011. And for this particular family, also known as definable functions in some all minimal structure, if you know all minimal structures, it's in RANEXP. So because of this all minimal structure property, you know they satisfy good uniform monotonic properties. And this is the fact that this is in an all minimal structure is verified by Vandendreis, McIntyre, and Marker a little earlier. So we have all the tools. Fortunately, we don't need to prepare them ourselves. We have all the tools. And what we do is just we put all the semi-algebraic sets of bounded complexity into a family. And then we just do integration and use the powerful tools. By these 5 people, we can prove the monotonicity lemma. And I think that's the end of my talk. So thank you so much for the attention.